welcome back to my channel. So last time we learned thermal EOS, which is for equation of state. And as the application of thermal EOS, we are going to discuss ideal gas law and van der Waals law today. So let's get it started. So the first is ideal gas law. So as it's called, ideal gas law. So it works the best for ideal gases. However, ideal gas does not really exist. But for a lot of times, ideal gas law is a great assumption for a lot of gases. So in order to use ideal gas law, the substance has to be in gas phase. So the common mistake is for H2O or for refrigerant, which is R134A. So unless I tell you that's a gas phase, or if you can determine they are in gas phase, otherwise you cannot use ideal gas law. But if the substance, they are air, they are oxygen, they are nitrogen, you can assume they are in gas phase, unless I tell you they're not. So there are a lot of formats for ideal gas law. One of the common ones is PV equals to RT. So P is pressure, V is a specific volume, R is a gas constant, and T is the temperature. And besides PV equals to RT, you could also have P equals to rho RT, which you move the specific volume to the right side of the equation, which is density. Or you could have a P capital V for volume equals to MRT. So if we are written as P little v equals to RT, then we don't need to deal with mass anymore. So in thermodynamics, most likely we use this form, P little v equals to RT. So we don't need to deal with mass anymore. So in this format, R is gas constant, and this gas constant is only substance dependent, and it's not depending on the pressure or temperature, and it's only depending on the substance. So for example, if the substance is air, then this is the R value for air. Let me show you how to get this gas constant. So here is the table that you can figure out the gas constant value. So like we said, it's only depending on the substance. For example, if it's air, then the number is 0.2870. And if it's argon, then the number is 0.2081. And if you screw down, such as for H2O, then the gas constant is 0.4615. And for R134A, the number is 0.08149. And the units of gas constant is kilojoule per kilogram per K. And we are going to use those units a lot in the future. All right, let's come back to our slides. And the last variant is T, which is for temperature. So for temperature in thermodynamics calculation, here is a trick. So you cannot directly use degree C, but you have to convert to Kelvin by adding 273. And a similar thing, you cannot directly use Fahrenheit, and you have to convert to Rankine temperature by adding 460. So this is for ideal gas law. So most likely, ideal gas law is a great assumption for a lot of gases, as long as the temperature and the pressure is not very high. Next one, let's take a look at van der Waals gas law. So as another application of thermal EOS, we could also model gases by using van der Waals gas law. Then this is the expression. So for ideal gas law, that's PV equals to RT. Then this one is kind of similar. So it's P times V, but adding something and subtracting something. So it's pretty similar, like PV equals to RT. Then that's A and B here, they are constants that you can calculate. So TCR is the critical temperature of the substance, and P sub CR is the critical pressure of that specific substance. Then I'm going to show you how to find critical temperature and the critical pressure of a specific substance. This is the table that we just used. Then as you can see, for each substance, we have the critical temperature and the critical pressure. So you can look up all the values from here. We have for air, for argon, if you scroll down, we have for H2O and for refrigerant. So this is critical temperature and the critical pressure. Keep in mind the units on the table for critical pressure is MPa, megapascal, which is 10 to 6 of Pascal. So this is van der Waals gas law. So as we said, this is another assumption for modeling gases. So let's take a look at an example by modeling R134A as a gas by using van der Waals gas law and ideal gas law. So for this R134A, we know it's in gas phase, and it has a pressure and a specific volume, and they ask us to find the temperature by modeling with van der Waals gas law, and also find the temperature by modeling with ideal gas law. Then compare the percentage air by using two different methods. So let's take a look. So for van der Waals gas law, this is the function. Now we're going to calculate A and B value. So if we go to the table that I just showed you, we can find the critical pressure, critical temperature, and the R value for R134A as the substance. Then we can calculate A and B value. Then we can plug them in. Then we can calculate temperature, which is 244 K. And we could also model this R134A by using ideal gas law, PV equals to RT. And it turns out to be our temperature is 239 K. Then the percentage difference is about 2.4%. All right, this is all we have for ideal gas law and van der Waals law. Thanks for watching. We'll see you next time. Bye.